morning to one and all. I welcome you all for the Thermodynamics course. Myself, Arun Kumar K, Assistant Professor, Aeronautical Department from MLR Institute of Technology, Hyderabad. So in the previous lecture, we discussed about steady flow process, right, which is applicable with respect to the open system. And in today's lecture, we are going to derive the energy equation for the steady flow process. Right. So in simply, we can able to say that is SFEE, steady flow energy equation. Right. So in addition to that, actually we are going to discuss about the mass balance equation also. So if I use the term steady, then obviously we supposed to get the mass balance equation also. Right. So with respect to the time taken, the flow property remains same. So for that also, actually we are going to derive the mass balance equation as well as the energy balance equation. That is what is important for solving numerical problems with respect to the open system when it is considered as a steady flow process. We'll start with the mass balance equation. See, we know that with respect to the steady flow process, right? So the mass flow rate of inlet is always equal to the mass flow rate of outlet. Right? So that is what actually we have considered for the steady condition. See, the term steady is nothing but actually with respect to the inlet, whatever the flow property, irrespective of the time, it is always remains constant. Then whatever the mass actually we have considered before starting the process, after completion of the process also, the mass remains same. Right? So we know that it is nothing but actually we are having the flow conditions, right? So we are having inlet over here and we are having outlet over here. For example, we can able to consider in this way. See, I have considered this is my working substance with respect to the open system, right? So I have considered M equal to, for example, M equal to 1 kg if I consider. So for the steady flow process, so for the flow process is nothing but actually the mass transfer takes place through the system. So the mass is also transferring along with the energy parameter. So what is that state actually? So before starting the process, what are the mass I'm having? After the completion of the process also, I'm having the same mass. So which means always with respect to the inlet flow rate is equal to the outlet flow rate. So this is your inlet state with respect to 1 and this is your outlet cross sectional area state with respect to 2, right? So the mass flow rate with respect to the inlet is equal to mass flow rate with respect to the outlet. So that is what the simple steady state conditions we are having, right? So if you want to apply with respect to the equations, see, listen here. So the mass balance or the steady conditions is achieved when the mass flow rate at the inlet equals to the mass flow rate at the exit, right? So there actually I can able to apply the balance equation with respect to the mass. That is what we call it as a mass balance equation, right? So the equation is nothing but simple one. Actually we are having m dot I equal to m dot E. So I is nothing but inlet and E is nothing but exit, right? So in some other textbook also you can refer actually m dot 1 equal to m dot 2, right? M dot 2. So what is this unit actually we are having? Mass flow rate, kilogram per second, kg per second, right? So this is what actually we call it as the mass balance equation. So the mass is balanced actually with respect to the open system, steady open system, right? See, with respect to the continuity equation also actually I can able to further simplify this equation, right? So from the continuity equations actually we are having m dot equal to actually we are having with respect to rho a v. V or we can able to consider as velocity. Here in the thermodynamics, V is nothing but volume. We'll consider C, right? So rho a C. According to the continuity equations, we are having the mass flow rate equal to depends upon rho a C, right? Rho is nothing but the density of the working substance, and A is nothing but with respect to the inlet or exit conditions, and C is nothing but with respect to, say, for example, C1 over here. Here it is A1. Over here, C2 and A2. Right? Always we know that the rho density of the working substance for a while, for the steady conditions or for the ideal conditions, we'll consider rho 1 equal to rho 2. In that way, we will consider. But it is also depends upon with respect to the changes in the temperature, right? So with this actually continuity equations, I can able to substitute over here. So I can able to get rho A1 C1 equal to rho 2, right? A2 and C2. So like that actually I can able to apply the mass balance equation. So this is what the mass balance statement we are having, right? And when we move to the energy balance equation, right? So the energy balance is nothing but, see, for all thermodynamic systems, when it comes under open system, I supposed to consider mass transfer as well as energy transfer, right? That we are going to apply with respect to the steady condition. That is what actually we are doing. Got it? See, the energy balance also we can able to consider for the steady conditions, right? For the steady conditions, let me read out the statement over here. There is no accumulation of energy. That is what the energy balance we are having. There is no accumulation, but the energy transfer will take place, right? We can able to apply the heat energy to the system. We can able to extract work done from the system. So this multiple energy transfer takes place, but at the end of the completion of the process, right, there is no accumulation of energy. This is what actually for the steady conditions it is applicable. Why? Because always for the steady in the sense, the property with respect to the time taken already we discussed remains constant, right? So obviously the energy parameter also should remains constant irrespective of process, right? Initial and final state or during the process. Got it? So which means by conservation of energy, we know that. So what are the energy we are applied? So which means obviously that is converted into other form of energy, which is not stored inside the system, right? So this is applicable for the steady condition. So you see that the total rate of, right, for steady in the sense with respect to time taken, I said it is constant. So always the rate is nothing but with respect to the time taken, right? So the total rate of flow of all energy streams in the sense we are having kinetic energy, we are having potential energy, right? And we are having internal energy and we are having a flow energy. So this internal plus flow is nothing but we call it as enthalpy, right? So all these energy entering the control volume, right? Entering the control volume is nothing but the system which we consider must equal to the total rate of flow of all energy streams leaving the control volume. Then only there will be no accumulation of energy. This will be applicable for the steady conditions, right? How we assumed with respect to the matter, right? Working substance. The same thing actually we supposed to apply with respect to the energy also, right? But as I said, the energy transfer takes place, but the accumulation of energy into the system nil, right? So that is what this energy balance equations V states. See, for the flow system actually we are having already we discussed about what are the kind of energy parameters we supposed to consider with respect to the flow system, right? So we know that with respect to the C1 over here and this is C2 over here. With respect to C1 we are having certain kinetic energy, and with respect to C2 we are having certain kinetic energy which leaving the system, right? So which is nothing but half mv square we are having, and apart from that the datum level also actually we are having over here. The datum level also we are having. This is Z1 and consider this as Z2, right? So because of this datum level also the system possesses a certain potential energy also. See, in the closed system we have assumed only heat transfer, that is Q. So Q is transferring to the system, that is what desirable as I said, right? So for all heat engines this is what the desirable one, and we are extracting the work done from the system. Extracting the mechanical work done, displacement work done is nothing but mechanical work done from the system, that is also a desirable one, right? And because of this flow, right, open system, because of this mass transfer, what is taking place actually, flow energy is taking place, VdP. PdV is nothing but displacement work done, VdP is nothing but we call it as flow work done, right? and see V dP we are having, and this V dP plus we are having the already internal energy with respect to before starting the process, right? 1, and after completion of the process 2, we'll consider in that way, right? So what is happening? U1, right? V1 into dP. So V1 will be remains, the control volume will be same, but the pressure get changes, right? So that leads to the flow energy. This combined V dP plus U is nothing but we call it as enthalpy, right? So we are having the enthalpy parameter, energy parameter, we are having kinetic energy parameter, we are having potential energy, and we are having heat energy, right? And I'm having mechanical work done with respect to the turbine or with respect to reciprocating components, right? I can able to get the mechanical work done. So these are all the energy parameters we supposed to consider for the thermodynamic flow system, right? See, the thermodynamic flow system we have considered only Q, internal energy, heat energy, internal energy, and work done, displacement work done, right? But whereas with respect to this open system, we supposed to consider all these energy parameters, right? So according to this statement, what is that statement? Actually, we are having the total rate of flow of all energy streams. So with respect to the time taken, I supposed to say, right? So the energy parameter is nothing but we can say joule or kilojoule, right? So kilojoule per time taken. So joule per second is nothing but actually we call it as kilowatt, right? So with respect to time taken, I can able to say. So the energy streams is nothing but actually we can able to say. So if it is closed system, I used to say kilojoule per kilogram or joule per kilogram, right? Similarly, with respect to this flow system, as well as with respect to steady condition, the rate will be remains same. So with respect to the time taken, so kilojoule per second is nothing but actually we call it as the flow rate of all energy streams, right? Which entering and which leaving, that we'll consider, right? So which is equal to with respect to the leaving the system. So in that way, I can able to frame the equations. So these are the energy terms in flow process. See, listen here. This is what we discussed just now. So internal energy. Then after that, we are having flow energy, right? So with respect to that internal energy and flow energy, we call it as enthalpy, right? And then actually we are having kinetic energy, and then we are having the potential energy, right? So these are all the conditions actually we supposed to consider, right? See, with respect to this Q1, we have supplied the heat energy to the system. So for thermodynamic, obviously we supposed to consider the heat energy, and after that we have extracted the mechanical work done also, right? So these are the energy parameters actually we are having with respect to the open system. See, this enthalpy is nothing but this is applicable only with respect to the open system for the flow process, right? If it is non-flow process, then that is what actually enthalpy is nothing but the flow energy will be 0 for closed system. So H equal to U. So internal energy becomes your enthalpy, right? Yes. So with respect to that statement, what is that statement actually we got? We got the statement as the rate of flow of energy streams entering the system is equal to energy streams leaving the system, right? See, listen here. This is actually we got here dot actually I have mentioned. So here also we supposed to mention with respect to the dot, right? See, obviously before framing this equation, I supposed to mention in terms of m dot 1 into u1. M dot 1 actually I supposed to mention this as m dot 1 and this is m dot 2. But we know that as per mass balance, we are having m dot 1 equal to m dot 2. So with that actually I can able to neglect those things. So I can able to easily convert the equation with respect to only the energy parameters we are having in terms of joule per kilogram or kilojoule per kilogram. Got it? See here, this is what actually we are having. U1 plus P1 V1. That is what actually we call it as enthalpy. That is what we are having H1. Right? And the potential energy is nothing but mgh or mgz. Right? So we are having m into z into z. So m actually we have taken common. Well, because for mass balance already we know that. Right? And V1 square by 2 or C1 square by 2, whatever it may be. Right? It's in some textbook actually the velocity used to mention in terms of V, right? As well as C also. Got it? Right. Plus Q dot. Q dot is nothing but actually we are having in terms of Dot is nothing but with respect to always rate, m dot and q dot, right? So the rate in the sense with respect to the time taken, right? So up to here actually we are having in terms of everything in terms of watt or kilowatt, right? Watt or kilowatt. Why? Because H always depends upon Cp and Cv. Cp is nothing but we are having 1.005 in terms of for air actually I'll consider 1.005 kilojoule per kilogram Kelvin. So that is the kilo actually mere we are having with respect to the Cp. So obviously we'll get in terms of more than three digits or 4 digits. That is why I used to say with respect to kilowatt or watt also, no problem, right? See, after that the mass of the fluid is taken as unity, or we can say for the steady conditions it is remains same, right? So that I can able to neglect it. So I can able to get the equation in terms of only H1 plus ZZ1 plus V1 square by 2 plus, see, instead of rate actually we just mentioned in terms of Q of 122, or you just mention this as capital Q, that's it. No need to mention with respect to dot, right? So here also see W dot is nothing but we are having in terms of kilowatt. Here W is nothing but actually I have taken in terms of, why? Because all units should be same, right? Then only I can able to sum up it. See, this is also we are having in terms of joule per kilogram. So in this way actually I supposed to consider with respect to the steady state conditions, and this is applicable for the energy balance equation, right? So with that actually we can able to simplify for the further various engineering components. Got it? So like that actually we are having we can able to apply this energy balance equation. Various thermodynamic engineering components we can able to apply, like a boiler we can apply, condenser we can apply, right? And we can able to apply turbines, nozzle, inlets, right? So like that actually we can able to apply with respect to the various components. So this is what your energy balance equation, simplified energy balance equation we are having, right? So we are having in terms of different forms actually we are having. See, we can able to mention with respect to m also. With respect to, instead of m dot, we can able to mention with respect to m also. M is nothing but actually we are having only in terms of kilogram, right? Got it? So we are having only with respect to kilogram in the sense. So the kilogram get cancelled. We are having in terms of, if it is m, say for example, if it is m dot, I said kilowatt. If it is m, actually it becomes actually only with respect to kilojoule, right? So if it is divided by m, actually we are having, what is that actually? By kilogram, kilojoule per kilogram or joule per kilogram. So kilo is nothing but a mere value we are having, right? So this is what the simplified energy balance equation we are having, right? See, after that actually where we can able to apply this steady flow energy equation, right? So why? Because in the mass balance equation also we can able to apply, but the major thing is nothing but the energy parameters we supposed to consider, right? See, all engineering plans actually we can able to apply. So the few examples actually I can able to give the boiler, or we can able to say the combustion chamber, the turbines, and then compressor we are having, right? And after that we are having nozzle, and we are having condenser. Got it? So in this way actually we can able to apply with respect to the various engineering components. Say for example, for applying the steady flow energy equation for the boiler, what are the consideration actually I supposed to consider? See, in the boiler actually we are adding heat energy. We are adding heat energy, right? So from the boiler, any mechanical devices are there to extract the work done. We are having after the boiler actually, say for example, if it is steam power plant or any power plants, we are having after the boiler, we are having the turbine. So only if I consider the boiler, there is no work done. So work done will be, mechanical work done will be 0, right? Flow work done will be there. Flow energy will be there. So if I have the flow energy, why? Because it comes under flow process. So if I have the flow energy system, then obviously I supposed to consider enthalpy. So enthalpy I supposed to consider, right? So Q I supposed to consider, H I supposed to consider, and what about the potential energy, and what about the kinetic energy, right? So if it is kinetic energies are negligible, then we can able to neglect the kinetic energy. And the datum level between the inlet of the boiler and outlet of the boiler is very less when compared with the sea level, right? Say for example, Z1 equal to for example 30 meter, and Z2 equal to we are having in terms of 31 meter. So with respect to these changes, actually we are having only in terms of 1 meter. So obviously we are having the entering and leaving is nothing but actually inlet and exit is nothing but we can able to neglect it. So like that we can able to apply with respect to the various engineering components. See, but in the numerical problem they provided with particular values of kinetic energy or potential energy, we supposed to consider that. This is what actually whatever I said is nothing but simplified form. Right? So like that we can able to apply for the other components also. For example, turbine. For the turbine, the mechanical work done is nothing but we are extracting. In the turbine, separate any heat energy process we are adding, nothing, right? So Q we supposed to neglect it. Right? And because of the flow, what is happening actually, internal energy will be there. Why? Because the working substance is flow taking place, right? So obviously we supposed to consider the H also, right? So like that we supposed to consider with respect to the various engineering components. Got it? So this is what the various applications of steady flow energy equations we are having with respect to various engineering components, right? Thank you one and all. We'll discuss the numerical problem in the next lecture. Thank you.